Welcome to this video on solving problems using bond energy and enthalpy values. Now here is an example of a molecule. It's a chloromethane molecule, and there are two types of bonds. There's carbon-hydrogen bonds, and we've got an associated energy here of 413 kilojoules. That's how much per mole. That's how much energy it would take to break a carbon to hydrogen, on average, a carbon to hydrogen bond across all of the molecules. What is the average energy it would take to break that bond? And then we have a carbon to chlorine bond, and here is the energy it would take to break the carbon to chlorine bond. It's 327 kilojoules per mole. So we're going to use these bond energies to solve problems about the energy that's involved, either in unknown bond energies or the enthalpy of a reaction. Okay, so the first problem we're going to look at here is how to calculate the enthalpy of a reaction when we're given the bond energies. Now this problem specifically, it says use the bond energies on the right. So we've got a table with the associated energies to break each bond in kilojoules per mole. Use the bond energies on the right to calculate the delta, the enthalpy of the reaction, its standard enthalpy of reaction for the following reaction. So the reaction has been, we've drawn out the actual bonds in each of these molecules here. So we've got a methane molecule, two oxygen molecules. They form two water molecules and one carbon dioxide molecule. Now the reason that we've drawn out the bonds, actual bonds in these, so we can work out what bonds have been broken and what bonds have been formed. So if I want to solve this problem, the easiest way to do this is to use the following equation. That is, the enthalpy for the reaction equals the total sum of all of the bonds broken minus the sum of all of the bonds formed. So we're going to have to tabulate all of the bonds that are broken and then subtract from the table the bonds that are formed. Now the way that I do this is I usually just sketch a table. So I've set it out in a table here so we can see in the video. On the left I'm going to account for all the bonds that are broken, and on the right all of the bonds formed. So let's start and do this. So quickly, before we just carry out the calculation here and account for all of these values, let's look at what's happening. So what's actually physically happening here is we have a methane molecule and we have two oxygen molecules. And what we're going to do is we're going to break all of the bonds in the methane molecule. That's 4 carbon to hydrogen bonds, and we're going to break 2 oxygen to oxygen bonds that are double bonds in the oxygen molecules. We're then going to take the atoms and we're going to put them together in a different way. We're going to form a water molecule like this, and we're going to form a second water molecule like this, and then with the last 2 oxygens and the carbon, we're going to form a carbon dioxide molecule. And notice what we did is we formed 4 oxygen to hydrogen bonds and 2 carbon to double bond oxygen bonds. Okay, so that's what we're going to do. Let's see if we can now solve this problem, solve this equation. So we have here our 4 energies that we're going to use, the 4 different types of bonds on a table. They will be given to you. Here's our where we're going to tally everything up. Okay, let's go through and work out what bonds are actually broken. So we've got 1, 2, 3, 4 carbon to hydrogen bonds. So 4 carbon to hydrogen bonds. They are 413 kilojoules per mole each, so that's going to be 4 times 413 gives us 1652. Now we're going to work out, okay, we've also got to break the oxygen bonds here, so we've got 2 oxygen to oxygen double bonds. Now those are represented by an oxygen to oxygen double bond here. If you see in a table just an oxygen to oxygen bond, that is not what we're talking about. It has to be specifically the double bond, and we have an energy given for the double bond. It's 498. There are 2 oxygen to oxygen double bonds broken, so that here is 2 times 498, which gives us a value of 996. Now those are all of the bonds that are broken. The reason why I put a line through each specific bond is I'm making sure I haven't missed any when I go back and I scan it later. I haven't missed any. That's the total of all the bonds broken. So now we have 2,648 kilojoules per mole of energy for the bonds broken. Okay, let's look at the bonds formed. What bonds have we formed in this reaction? Well, we've formed this bond here, hydrogen to oxygen, another hydrogen to oxygen, or oxygen to hydrogen bond, we might say, a third one, and a fourth one. So we have 4 oxygen to hydrogen bonds. So 4 oxygen to hydrogen bonds. We can see it from the table here, the value is 467. So we're going to go ahead and multiply 4 times 467, where we get a value of 1868. The other bonds that we have formed are oxygen to carbon bonds. Again, I caution you, because this is a double bond here, you have to find the value that is an actual double bond and not a carbon to oxygen single bond and multiply by 2. But because this is a carbon dioxide, there are 2 carbon to oxygen bonds. So we're going to multiply the number of these bonds by 2. And the value here is 745, and I'm going to multiply that by 2. That gives us an answer of 1490. So the total energy in forming the bonds is 3,358. Now remember, we had this equation here that the enthalpy of the reaction equals the total of the bonds broken, which is 2,648, minus the total of the bonds formed, which is 3,358. We substitute those values in, and then we solve, and we get the answer of the enthalpy for this reaction is 710 kilojoules per mole. And that's how we calculate the enthalpy of a reaction when we are given the bond values. Okay, so we can also calculate an unknown bond energy if we know the enthalpy of the reaction, and we also know the bond values. So the enthalpy for this reaction here, the delta R for this reaction, is minus 102 kilojoules per mole. We're given some bond energies, but they want us to find the unknown one of chlorine to chlorine. We're given the carbon to hydrogen bond energy, the hydrogen to chlorine bond energy, and the carbon to chlorine bond energy. Again, we're going to use a table here, but just let's have a look at what's actually happening in this reaction. So in this reaction, we actually have a methane molecule and a chlorine molecule that we are going to react together to produce the chloromethane molecule and the hydrochlorine molecule. Now, what's actually happening here is we're going to break this bond here between the carbon and the hydrogen, but notice that that's the only bond we need to break on this methane molecule, because we are going to we're going to keep these other carbon to hydrogen bonds intact. And I'm going to break this chlorine to chlorine bond, because what I'm essentially going to do is then take one of the broken chlorines and attach it. So the new bond I'm forming is the carbon to chlorine bond, and then I'm going to put together the hydrogen and the chlorine again, and the new bond I'm going to produce here is the hydrogen to chlorine. So I've broken 2 bonds and formed 2 bonds. I don't have to break all of the other carbon to hydrogen bonds. Okay, so let's see if we can carry out this calculation now. So the first thing we're going to do again is identify the bonds that have been broken. And remember, if we scan from the left-hand side to the right-hand side, we can see that in this methane molecule, there is actually only the carbon to hydrogen bond that has been broken, because all of the other 3 remain in place. So we're going to write that down. 1 carbon to hydrogen bond. Here we see it's worth 413 kilojoules per mole. So we're going to write down 413. And we get the total energy here of 413 kilojoules. And then we're going to see that we break another bond. That's the chlorine to chlorine bond. And when we look over here, we have 327. Sorry, we don't have, because the chlorine to chlorine bond, we have that is X. We don't know what this one is. This is the energy we're trying to find out. So now when we do the total bonds broken, we've got a wee algebraic expression here. We've got 413 plus X. So the bonds formed, remember these 3 bonds were intact, so we're just forming here the carbon chlorine bond, and the carbon chlorine bond is 327. And then so that total amount of energy here is 327. And then what we're going to do here is also form this hydrogen chlorine bond, which is 428. 1 times 428. We add these together and we get 755. So now we have the total bonds broken and the total bonds formed. We can now substitute into our equation, our enthalpy equation. But remember, we also have this value at the top for enthalpy, negative 102. So we're going to go ahead and substitute that in with our delta RHs. And then we're going to put the bonds broken and the bonds form in their correct place. And we end up with this equation here. So minus 102 equals, brackets here, 413 plus x minus 755. We're going to group like terms here on the right hand side. So I do that by taking the 755 away from the 413. We get 342. So x minus 342. Again, if we put those terms together, it's x equals if I put x on one side by itself, it's minus 102 plus 342. Remember, when we take the 342 to the other side of the equation, the negative becomes positive. I resolve this equation and my answer here is 240 kilojoules per mole. Now, does that seem like a reasonable value? Well, up here, when we see that a carbon to chlorine bond is 329 and the other ones are 400, it's in the hundreds. It's at 240 isn't out of the it's definitely a possibility, so we're quite comfortable with that. If this had been a number like 52 or 2000 or something like that, we would have known we've made a significant mistake, would have gone through and checked our answers. This is how we calculate the bond energy when we know the enthalpy and we know some of the other bond energies. Hopefully this video has been helpful to helping you resolve problems to do with bond energies and enthalpies of reaction. Best of luck with your chemistry study.